So the work I am going to be presenting today is done in collaboration with Rio from Clarkson University and Adelson from here at Northwestern. And this was published in PRX just a couple of weeks ago. The butterfly effect, which is the defining property of chaos, refers to sensitive dependence on initial conditions, where two copies of the same system with slightly different initial conditions initially start out following a trajectories that are almost identical, but they start to diverge away from each other and eventually follows entirely different dynamics. So what would be the network analog of this behavior? For networks that mediate dynamical process, like road networks, power grid networks, neuronal networks, metabolic networks, food web networks, and social networks, just to name a few, the question is the following. If the structure of one of those networks are slightly perturbed, would the dynamical process change slightly also? Or does it change by a lot? In other words, is there a sensitive dependence of the network dynamics on the network structure? So to formalize this question in a more general setting, more rigorous setting, I'm going to consider broad class of networks, in fact, with dynamics that are described by this equation, where f is a nonlinear function in general, and the dependence on y variables are the same for all I. And h sub ij is the coupling function, which we assume to be diffusive. And the proportionality constant that appears in this diffusivity assumption contains the coupling matrix that encodes the network structure. And we consider a state that we call network homogeneous state, in which all the nodes, the states of all nodes, are homogeneous at any point in time. And this is a kind of formulation that is slightly different from what has been done in the literature, particularly by this paper by Fink and colleagues. And our formulation has the advantage that the diffusivity assumption is rigorous mathematically and also intuitive, and there's a clear connection to the coupling matrix that encodes the network structure. So among all the networks with a given number of nodes and links, the interesting set of networks are those that maximize the stability of the network homogeneous state. Now, this stability can be measured by rate of convergence, and this stability can be computed, analyzed by the well-known method of master stability function approach, developed by Pecora and Carroll back in 1998, by basically extending that to this broad class of systems. And the important thing about this approach is that the stability through this stability function can be determined by the eigenvalues of the Laplacian matrix L that also encodes the network structure and is defined by these equations. So our main result is that when you optimize a network for the stability, we often observe that the optimized stability exhibits sensitive dependence on the network structure. Whether you actually see sensitivity or not depends on the class of networks and also the type of perturbations. On the one hand, undirected networks are sensitive to unweighted perturbations like link removal or node addition in large networks. But they're not sensitive to weighted perturbations, namely small changes in link weights. On the other hand, directed networks are sensitive to weighted perturbations, but not to unweighted perturbations. By sensitivity here, I mean that the change in, for example, the eigenvalues that determine stability, when you look at it as a function of the change in the network structure, it shows this type of cusp behavior. So let's first look at undirected networks under unweighted perturbations. For undirected networks, the optimization that I just mentioned, it happens that you can reduce the problem to the maximization of lambda 2, which is known as algebraic connectivity, and it's defined as the smallest Laplacian eigenvalue among those that are not identically zero. So what kind of network structure actually maximizes lambda 2? Well, it turns out that the class of networks that are characterized by being uniform, complete, and multipartite, or we call it UCM networks. It turns out these networks we can prove that they are the unique maximizer of lambda 2. Multipartite here means that the network can be organized into groups, and there are only links between groups and no links within any of the groups. Complete means that all possible links between groups are actually there, and uniform basically just means that the size of the groups are all the same. The key property that makes this class of network optimal can be understood better in terms of what's known as the complement. The complement of a given network is a network which has all the links that the original network doesn't have, but has all the links. I'm sorry, let me try again. The complement of a given network is a network that doesn't have any links that the original network has, but has all the links that the original network doesn't have. So here's an example of a UCM network, and the complement looks like this. And you can see that they consist of isolated complete graphs of the same size. And the key property that I was talking about, in fact, is that the maximum size of the connected component in the complement is as small as it can be. Now, this property, turns out, can be used to define a broader class of network that we call MCC networks for having the minimum possible size of the largest components in their complement. So here's an example that's it has the same number of nodes as the network in the previous slide, but one fewer link. And in this case, it has some links denoted by blue line here that are within a group. And complement of this network looks like this, and you see that the components are not quite complete because there are some missing links denoted by blue dashed lines, and the size of the components are not necessarily the same. So by definition, the maximum size of these connected components in the complement are as small as it can be. And this class of network happens that we can prove something. It's not necessarily globally optimal for lambda 2, but we can prove that they are always locally optimal, in the sense that the rewiring of any single link in an MCC network can never increase lambda 2. So it's in this class of network that we observe sensitivity to unweighted perturbations. So if you look at lambda 2 as a function of density of links, and you change it, and that's the unweighted perturbations, changing the number of links basically, it looks like this for the networks of size 20, and it has this sort of cusp-like behavior. And this, as you make the size of the network larger, you see that this cusp actually becomes sharper and sharper, and in the limit of n going to infinity, it becomes a true cusp with infinite derivative on the left side of this point. And in fact, there are infinitely many points like that. All of this is based on the fact that we can derive explicit formula for lambda 2 for finite n. And you can take the limit of n going to infinity in this formula and get a formula for the infinite derivative, infinite n case. And this can be used to prove that you actually have infinite derivative at infinitely many points. So let's now turn to directed networks under weighted perturbations. In this case, we consider perturbations of the following form: A, which is the adjacency matrix, plus little delta, which measures the perturbation size, times delta A, which is a constant matrix that determines the direction of perturbation in the space of all matrices. The resulting change in Laplacian eigenvalues, which determines stability, we denote by delta lambda. And this delta lambda, we find that they scale on the generic perturbations with respect to delta, the small perturbation size, with the exponent equal to 1 over beta j, where beta j is defined as the number of repetitions of lambda associated with its jth eigenvector. In other words, beta j is the size of the jth diagonal block associated with lambda in the Jordan canonical form of the Laplacian matrix. So the largest among beta j is called the geometric degeneracy, and we denote it by beta, and this determines the sensitivity. And the criteria is very simple. In fact, if beta is equal to 1, the scaling implies that you have a linear behavior around this point. And if beta is bigger, then you have a cusp behavior as a result of the scaling. So let's look at some examples. Here is a bunch of networks of size 20, and all of them actually has the same eigenvalues. Other than the identically zero eigenvalue, you have just 3, but it's repeated 19 times. But beta, the geometric degeneracy, actually varies from 1 to 19. 19 is the maximum value you could have in this network. So I'm going to show you the plots of change in Laplacian eigenvalue, in particular lambda 2, as a function of perturbation size delta. And for beta equal to 1 network, you see a linear behavior. But for other values of beta, you see a cusp as a result of scaling. And for larger values of beta, the sensitivity is actually a lot more drastic. To see how it works for other eigenvalues besides the algebraic connectivity, let's take this particular network, beta equal to 7. It has eigenvalues 3 repeated 19 times, as I mentioned earlier. I'll be wrapping up soon. The Jordan canonical form of this of the Laplacian matrix looks like this and has the block diagonal form like that. And the size of them determines those beta j's. And as our results, here's an illustration of our results. that shows that the scaling that I mentioned earlier actually is followed by individual eigenvalues that comes out of the degenerate eigenvalue 3. So optimization. I've shown you optimization can lead to two kinds of sensitivity, and this phenomena can be interpreted as a parameter counterpart of sensitive dependence you see in low-dimensional chaotic systems. There it's the small change of parameters that leads to large change in dynamical behavior. And in our case of network analog, small change in the network parameter leads to large changes in the dynamical behavior of the network system. So all of this, I skipped over a lot of mathematical details, but all of them are in a relatively long paper that we published in PRX. And if you want the short version in the video form of the explanation of all of this, we also created a YouTube video. So thank you very much for your attention.